In this Mathematica Sessions video, which is number 10 of the series on discrete math, we are going to be investigating combinatorics, or what I call counting, and how that applies to probability. If you're interested in that, keep watching. We're going to do combinatorics, and I like to call that counting. Hello, yeah, I see you in the chat. Okay, thanks. So yeah, I like to call this counting because basically you're counting numbers of possibilities essentially, and that's useful in terms of counting probabilities, right? So the chance that something can happen. All right, so we've got a few questions to go through today. Our first question is this one that I've got here. So it says the drama club is auditioning for a Romeo and a Juliet. 6 people are auditioning for Romeo. 8 people are auditioning for Juliet. How many ways can the director cast for the lead couple? Okay. Now you can see that I've got some code here. I'll talk about that in a moment. Of course, you don't need to know that, but it helps bring this question to life a little bit. Okay, so the way I like to think of this kind of problem is we've got, and so I'll often draw like 2 spaces, something like this, to remind myself that there are 2 places that we've got to fill, a Romeo and a Juliet. Now, above this, by hand, I might note to myself that I've got a Juliet 1. Hang on, I want to start with Romeo's, don't I? Romeo 1. I've got a Romeo 2 to choose from, etc. And then I've got a Romeo 6 to choose from. Okay, and I also have something similar for the Juliets. I've got a Juliet 1, I have a Juliet 2, and so on, and there's up to a Juliet number 8. Okay, in 2 places to fill. Right, 1 and 2. All right, so considering all the possibilities, I want to make this real for you. So what I've done is I've got on Google Images, and I've just typed in Romeo. Okay, and I'll show you what I found here. So by displaying, what I'm doing here is I'm essentially putting into memory some images that I found for potential Romeos. And so I'm doing that by combining strings and then basically importing an image that I've called r1.jpg, right? So this procedure here allows me to iterate from 1 to 6 over those and import each of those and call them R1, R2, R3, etc. So they're just images, right? And so the same for Juliets. I did the same for Juliets. I got onto Google Images, I typed in Juliet, and I found 8 Juliets. And so I'm going to put those into memory here. Now, what I'm doing here is I'm just listing all of the possible pairs, right? So R1 through 6, J1 through 6, sorry, through 8. So I'm iterating over I and K. And then what I'm doing is I'm getting rid of the extra brackets with this command. And then I'm breaking them up into pairs again because this procedure inside right here gives me lists of lists. But I really want just one list of pairs. Okay, and then here I count how many do I have. And then this command gives me a random number, integer that is, from 1 to n, puts that in memory as m, and then finally I'm going to index out of the set S, or the array S here, which is the collection of all those images. And then the final one is the probability that I get a particular pair. So let me just show you what I do here. I'll take the semicolon off and I'll run that. Okay. I don't know what's going on, so I'll quit the kernel here and I'll run that again. As I can see, I've got an orange line there. Oh, I see. I've drawn here and I've not commented that out. So here we go. Let's try that again. Except it'll take a little bit of time because I've quit the kernel and now the kernel needs to initialize again. So we'll take a little breather while we wait for this. Okay, so here's one such possibility. Here's a Romeo and here's a Juliet. All right, so if I run this again, now I've got the same Romeo but a different Juliet. All right, let's run this again. Okay, here's another Romeo and another Juliet, and so on, right? I could get this pair, I could get this, and so on. Okay, now, so how do we do this theoretically? Basically, you just say how many possibilities can go in the first place, right? And that is 6. How many can go in the second place? That's 8. And so obviously we take their product, right? Because for every one of these Romeos, we've got 8 possible Juliets. So we're going to have 8 plus 8 plus 8 and so on, and 6 of these 8s, and that's 6 times 8. So of course 6 times 8 is 48. Okay, good. And the probability is 1 over 48 that we get, say, this particular pair of Romeo and Juliet. And that's about 2%, as we see there. About 2.1%, let's say. All right, any questions about that one? You can type in the chat too if you want to write there. All right, I guess that's good then. Let's move on. Now, the next question says, how many distinct arrangements can be made from the letters of the word Indrapili? Okay, now to understand this kind of problem, because the key here is that you've got several repeated letters. The L's are repeated, the O's are repeated, and the I's are repeated. So what do you do with those, right? Because we know how to take permutations, it's just factorial, but we've got the problem of these repeated letters where they're not distinguishable. So I suggest that we look at this from the point of view of the word door, because door is much simpler than Indrapili. Okay, so we've got 1 D, we've got 2 O's, and we've got 1 R. But you see what I've done here? I've labeled them O1 and O2. And so I want to take the permutations of this, right? And so that will be this one that I've called Q. And then I'm going to count how many there are. So let's just have a look here. Of course, you could do this by hand too, because there are very few of these. All right, so these are the possibilities here. So we've got D, O1, O2, D, O1, R, O2, and so on, right? And there are 24 of those. However, you know that the O1 and the O2 are the same, right? Because they're just O's. So what we've got to do, like how many do we have that say door, for example? Let's find another one. So I'll copy this out and let's put it right there. So door and door are the same. So how many ways can we have that? Well, two actually, right? We see 1, 2. There are two of these that say door. And the reason to see that from a theoretical point of view is that what we're doing here is we're taking all the O's and we're permuting those, right? And we have 2, and I'll just put factorial symbol there, 2 factorial, which is 2 of these. And in fact, for each arrangement, like for example, Doro, we have 2 Doros. Again, because there are 2 O's, and so we count 2 of those. Now, if we're counting 2 of each of these, we've got every one of them is doubled, right? So how many arrangements of each? How many distinct arrangements of the word door are there? Well, there are going to be 12, right? And so we can view this as, well, 4 factorial for the number of permutations, and then we divide by 2 factorial for the number of repeated letters, okay? Arrangements of the word door. All right, so given that we know that, now we're ready to tackle the word interpilly from the same point of view. All right, now if I would run the same thing here with interpilly, I believe this would just take forever. So I'll just show you now what's going on. Insufficient memory. Okay, that's because, no, I've cleared that. Yeah, I don't know why it's got insufficient memory, but it would take forever anyway. Okay. Oh, I see, because I've not commented this out. Okay, sure. I'll try that again. No, it's actually in a different cell, isn't it? Anyway, so let's look at this from a theoretical point of view. So we take the letters of the word interpilly, which we've got right here, right? Okay, so these are the letters of the word interpilly. Now, what is repeated? Right? How many letters do we have? Let's just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so then we should have 13 factorial. And remember, we need to divide by the factorial of the repeats. So there are 2 i's. So then that would be 2 factorial. And then how many O's are there? There are 4 O's. So 4 factorial, and then there are 2 L's. So 2 factorial. But you see I've done this with an exclamation mark, which is mathematical notation. However, if I want to do this in this language, to make that calculation run, I should write out the word factorial. 13, and then I'm dividing by the product of factorial 2, factorial 4, and factorial 2. Okay, so let's calculate this. So we get 64,864,800 arrangements of the letters of the word interpilly. All right, any questions? Okay, just pause anytime and ask your question if you have one. So the next one, how many distinct arrangements can be made from the letters of the word interpilly that begin with R and end with P? All right, so if we're beginning with R and ending with P, then, and I can see that I've got some clues on this in here. So basically what I've done here is I've deleted the R and the P from this list. And so I want to draw an image of what I'm talking about here. So begin with R. So basically I want to fix the R. Since I don't want that to be taken as code, I'll put a comment around it. Okay, so I fixed the R, then I've got a place there for a letter, a place for a letter, a place for a letter. How many of these are there? There will be 11 of these because that's 13 minus 2. So 5, 6, 7, 8, 9, 10, 11. And then our last letter should be a P. Okay, so basically we note that neither the R nor the P are repeated letters in the letters of the word interpilly. So basically then our problem is to look at the permutations of the letters of the word with R and P taken out, okay? Because the R and the P are fixed there. And so in that calculation, what I'm doing then is calculating 11 factorial and then divide by 2 factorial, 4 factorial, and 2 factorial, because we still have the L, the O, and the I's repeated, right? Except this time we have only 11 letters to shuffle up here, okay? So let's do this in code. I'll take this and I'll put it down here. Okay, and actually I don't have anything special to run here, so I'll comment that out too. And we'll just take this calculation, do it again, but with 11 factorial in the numerator. Okay, so this time we get 415,800 as the arrangements of the letters of the word Indrapili that begin with R and end with P. Okay, sure. Let's have a look at part C. How many distinct arrangements can be made from the letters of the word Indrapili that begin with I and end with Y? Okay, so we've got a similar situation. So copy and paste this, except what we're fixing now is an I in the front and a Y at the end. So how does this change things? Well, the Y is not repeated, the I is repeated, so we still have 11 letters to permute. However, this time, the I in this collection is not repeated. The O and the L are still repeated, so the calculation is similar, except it's basically this without the extra 2 factorial there. So what did we say? There are 2 L's and 4 O's. So I'll put 2 of L and 4 of O, which is why we have the 2 factorial, 4 factorial in the denominator. Okay, so let's calculate this. So we'll get rid of the last 2 factorial. Okay, and so this is a little bit greater than the last one. It's 831,600. Great. Okay, so next and last question in 2. How many distinct arrangements can be made from the letters of the word Indrapili that have all 4 O's next to each other? Okay, so to think about this, what you want to do is basically you're looking at this, right? Let's take that R and we'll shift it over. You're basically looking at the arrangements of this word where you've got to think of this collection of the 4 O's as a single letter, right? Okay, so let's say, now let's pick something that looks a little like an O. How about a theta, an uppercase theta? So I'll choose an uppercase theta. Where did it go? There. Let uppercase theta be equal to the collection or the string of the 4 O's. All right, so I'll put this around it so that I really mean the string. Then we rephrase the question to say how many distinct arrangements of the word this one, right? Where this is the uppercase theta. There. Okay, so now this is a lot easier question to answer. So we can answer that in counting first. So we've got 3, 6, 9. Are there 10 letters? Looks like it. So then it should be 10 factorial divided by, now what's repeated here? We've got L's repeated and we've got I's repeated. That looks to me like it's all that is repeated there. Yep. So 2 factorial and 2 factorial in the denominator there. Okay, I'll make this a comment so that we can start to calculate. And so I'll just take this, copy and paste it, and we'll change this to a 10 factorial, 2 factorial, and a 2 factorial, and we'll run that. So we've got 907,200 rearrangements of that. Okay, good. Are we ready to move on? Can you guys still hear me okay? Yep, thanks, Alwyn. All right, so this question 3 says there are 11 questions on the final exam, but you decide based on your successful grade for your mid-semester test that you will only do 5 of them. Well, that's really foolish, but anyway, you've got the choice to do that if you want to. How many combinations of questions are there which you could complete? All right, so let's draw ourselves a little diagram. So we've got 11 questions. So let's say we've got Q1, Q2, Q3, up to Q11 that we could do, right? Now, how many places do we have? Well, we have 5 different places that we could put these questions, right? Is that 5? It looks like 5. Okay, so for example, e.g., you could start with question 2, then you could do question 3, and then you could decide you want to do question 11 because it's easy, and then you want to decide to do question 5 and then question 9, for example. Okay, but when the marker goes and marks these questions, do they care what order that you did those? Well, no, of course not, right? It doesn't say to do that in any particular order. You can choose the order that you do those questions in. That's what perusal is for you to decide in which order you will do those questions, right? Among other things. Okay, so in other words, order doesn't matter here. So order of questions is irrelevant. Okay, so that should tell you what you're looking for is a combination. All right, so in other words, that's 11, choose 5. So 11, choose 5, and we use the binomial symbol for this. So I don't believe that I have, actually, you know what, I'll just use a vector notation for this. So I'll just put this one in to talk about that. So in other words, 11, choose 5 is the mathematical symbol for this. But what it means is, whoops, that's not what I wanted. Okay, so what this is equal to is 11 factorial divided by 11 minus 5 factorial divided by 5 factorial. So in other words, we take this one minus this one and place it there and take its factorial. The others, the numerator is the top one, and the other denominator is the 5 factorial taken from there. All right, so this is mathematical notation for that. Now, so why is it that? Well, if I go up here and think, I could have 11 possibilities that I put here, right? So 11 could go there. And then for each of those, I've got all the other possibilities. So 10 could go here. And then 9 could go here. 8 could go here, and 7 could go there. All right, now if we think about what this is, let's see, that's 11 factorial divided by 6 factorial, right? So 11 factorial divided by 6 factorial. Okay, but 6 factorial is 11 minus 5 factorial. All right, now this is permutations. And so we have to think about what happens when we shuffle up all these possibilities. Okay, permutations in which the order does matter. So it would be this, right? However, given that the order doesn't matter, we can shuffle each of those options that we get, and so it tells us then to divide that by the number of places we have. So we'll say combinations for this will be the same thing, but then we divide by 5 factorial. Okay, and so this is equal to 11 choose 5. Also, incidentally, that's a coefficient in the expansion, binomial expansion of, say, x plus y to the power of 11. Okay, so I'll make all of this a comment. And then we'll calculate this here. So I've got a couple of ways to do that. So I'll just show you that they're both the same. So I could write binomial 11 comma 5, or I could just calculate it all out and say factorial 11 divided by factorial 11 minus 5 and factorial 5. So we should get the same number in both cases here because they're equal, these two. So 462. All right, so 462 ways that you could do that exam if you were only going to do 5 of the 11 questions. Again, bad idea, do them all. Because markers can be generous. Even if you don't know everything you need to know, you can hope to get part marks, right? Okay. Good, so let's move on and talk about question 4, if you're ready. All right, so question 4. Now, clear some space, I'll scroll down to the right spot. Okay, 5 people are to be chosen from a group of 10 people to form a committee. All right, so again, I like to draw just to give myself a mental picture for what's going on. So 10 people, and then we've got these 5 places for them, right? Space this out a little bit. Okay, so 10 people going in 5 places to form a committee. Now, so that says the order doesn't matter, right? Doesn't matter where in which chair they sit on the committee, they're on the committee. So how many different committees of 5 can be chosen? Well, this one's very easy because it's just 11 choose 5, right? So I'll copy and paste this notation. Oh, hang on, 10 choose 5, that's what I should say. Thinking of this earlier question. So 10 choose 5. All right, and we'll calculate this, which I can just do by writing binomial, as you know. 10,5. All right, so let's get some numbers, and I seem to have forgotten to comment that out, so I'll do that. 252 possible committees of 5 people can be chosen from 10. Okay, great. So now let's have a look at the next one, which is a little bit more involved, right? Now we have constraints. amongst 10 people, we have Alice, Bob, Eve, and Oscar. Alice and Bob are extremely talkative during meetings. And so at most one of these two can be chosen. Eve and Oscar are inseparable. And so on a committee, a committee must either contain both or neither of Eve and Oscar. Okay, with these constraints, how many different 5-person committees can be formed? All right, just so we can visualize this for fun, here I've got Alice, here I've got a Bob, and here I've got Eve and Oscar, inseparable. Okay, so you kind of have to think of Eve and Oscar and Eve as one individual, right? One entity. All right, so given that, what we want to do here is think about these in terms of cases, right? So how many cases could we have? All right, so I'll copy this down below our nice images. Let's think about this here. All right, so talkative during meetings, so at most 2 of these. Now let's abbreviate these, right? So let's go case 1. What could we have? We could have A or B, right, as in Alice or Bob, because you can't have both. So you can have at most one of them. We could have no Eve and no Oscar, right, because they're inseparable. So that's one case. All right, another case, before we count these, let's just consider all the cases. So case 2 could be, let's say we have no Alice, no Bob, no Eve, and no Oscar. Okay, so that's our case 2. Sure. Okay, another case. What else could we have? Case 3. So we've considered all the no Eve and no Oscar. So now let's include Eve and Oscar. So let's say that we could have then A or B and Eve and Oscar. Okay, so that's another case. All right, and then I think our last case here, whoops, is here. So case 4 will be that we have A or B. Hang on, no A, and no B, but we do have Eve and Oscar. Okay, good. Now we have to fit these possibilities into 5 places. So what we want to do at this point, once we know all the cases, is we want to sort of visualize this, okay? So what I would suggest for case 1 then, so A or B, and for that we've got one place, okay? And then also we've got, so no Eve and Oscar, but how many places have we got left? For this we have another 4 places, right? Okay, so then this means now in this box here we can put Alice or Bob, right? And so that's 2 possibilities. And we're multiplying it, so 2 times. Now, in this case, since we don't have Eve or Oscar, and we're not considering Alice and Bob because we're considering Alice and Bob for this box, what do we have remaining? So 6 possibilities, right, to go in 4 places. And that's a choose. So then that is, we need the symbol. I should just keep that in memory. 2 times, and we have 6, choose 4. Because there are 4 places and 6 to choose from for these boxes. Okay, now to calculate that, let's just calculate it. So we can even do this by hand, I suppose. So we have 2 times 6 factorial. And then we are dividing by the difference between 6 and 4. So 6 minus 4 factorial. And then also dividing by 4 factorial. All right, so let's cancel 6 factorial, 6 times 5 times 4 factorial. So we can cancel the 4 factorial here in the denominator and express this as 6 times 5, sorry, having canceled the 4 factorial. All right, and so what we have here is now we're dividing by 2 factorial. Okay, but of course 2 factorial is 2. And so this is just 6 times 5, which is 30. Great, so that's case 1 counted. All right. Okay, so let's move on now to case 2. So in case 2, we have neither Alice nor Bob. And we have no Eve and no Oscar. Okay, so this time we have 5 places still, right? And how many can go in? Well, we've got 6 can go in these 5 places because we're taking out Alice, Bob, Eve, and Oscar. Okay, so given that, well, again, this is binomial symbol, so choose, but it's this time it's 6 choose 5. All right, so 6 choose 5, and let's simplify this by hand. Okay, so we have in the numerator 6 factorial, and then in the denominator we have 6 minus 5 factorial, and then another 5 factorial. And I'll put a bracket around that denominator just to make it clear. Okay, now this one here in 6 minus 5 is 1, so you can ignore that. And so this is equal to 6 times 5 factorial in the numerator divided by 5 factorial in the denominator. Now we can cancel that 5 factorial, and we find out that it's 6. Okay, good. So this is case 2 done. We have 6. Okay, now case 3, Alice or Bob. And so I can copy a little bit of what I've got up here. Right, part of the diagram, and then we also have, this is Eve and Oscar, right? So Eve and Oscar. Okay, so this one, I need to draw this a little bit differently, right? Because hang on. Yeah, okay, all good. So we fill this here. We fill this with Eve and Oscar, right? That inseparable pair right here. All right, so then here we've got 2 possibilities can go in this box. Oops, 2, this is fixed. And then in this, what do we have left? Well, we've got six other people that can go in 2 boxes. So this is 6 choose 2, right, for that spot. So calculating, this is 2 times 6 choose 2. Okay, and let's simplify that. So that's 2 times 6 factorial divided by 6 minus 2 factorial divided by 2 factorial, and we'll put a bracket around that denominator again. Okay, now let's simplify. So Righto. So this is 2 times 6 factorial. This is 4 factorial here. And so we want to express that numerator as 6 times 5 times 4 factorial so that we can cancel the 4 factorial here. Okay, so let's put another line in and do that cancellation. Canceling the 4 factorial from there. 2 factorial, of course, is just 2. And so we can cancel the 2 there, and we get 6 times 5 is 30. Okay, great. So last case. No Alice, no Bob, but even Oscar. All right, so this time we can view this as Eve and Oscar, those are fixed, and then we have 3 other places. But we cannot have an Alice or a Bob in these 3 other places. So we take out of the picture for candidates for these 3 places, we take out Alice, Bob, Eve, and Oscar. Eve and Oscar, of course, are there. So 6 can go here. All right, so that then is 6 going in 3 places, so that's 6 choose 3, right? And this is of course 1, so 1 times 6 choose 3, which is just 6 choose 3. Okay, now let's calculate that. So we've got 6 factorial divided by 6 minus 3 factorial divided by 3 factorial. Okay, now let's simplify this. So 6 factorial divided by 3 factorial divided by 3 factorial. So we can express this as 6 times 5 times 4 times 3 factorial in the numerator. And now let's simplify that, canceling the 3 factorial there with one of these. All right, and then so 3 factorial we know is 6. So we can cancel the 6, and we have 5 times 4 is 20. Okay, so now in total, how many possibilities are there? We just have to add all these up. So adding the 4 cases, the 4 case possibilities, what we have is, let's see, let's go up to the start. Case 1 was 30, case 2 is 6. So 30 plus 6 plus case 3 is 30, and then case 4 is 20. Okay, and so I don't want to run this. This should be easy enough to do in our heads, right? So 30 plus 6 is 36, plus 30 is 66, plus another 20 is 86. So 86 possibilities here to form a committee. To form the committee. Is it like that? Committee. Yep. Okay, good. Under those constraints. So with these constraints. Okay, good. So last question on here. What is the probability that none of Alice, Bob, Eve, and Oscar are on a committee given that a random committee of 5 is chosen subject to the constraints in part B? All right, so what we have to do is notice that this refers to, which case is it? None of Alice, Bob, Eve, or Oscar. So that's case 2, right? So just copy this and we'll paste it right here. Right, so we have 6. 6 ways to choose the committee without Alice, Bob, Eve, or Oscar. Okay, but the total number of committees subject to those constraints, that's 86. All right, so in other words, 8 over 86, sorry, 6 over 86, and we can just do some cancellation in our head, right? So that's 3 over, what's half of 86? It's 43. 43 is prime, so is 3. So that is reduced as a fraction, but let's just calculate this numerically. So 6 over 86 numerically. So that's a 6.9% chance, basically. But this number here is the probability, because remember, the probability is a number between 0 and 1. Okay.